Okay, without further ado, John Mays is the founder and author of many a Novare science resource. Novare started about 12 years ago. John taught full-time for many years at Regent School of Austin and started developing his own resources while he was teaching there. And it started turning into a much bigger project and calling for him to produce high quality, mastery oriented science curriculum for students in middle and high school. Now Novare is a part of Classical Academic Press. We have been a part of CAP for the past year and a half. And there, John is the director of science curriculum and continues to write for Novare, to speak, and to also direct the work of our other authors, such as our earth science author and our biology authors. He's also had a lot of experience in the classroom with labs, which is what he's going to talk to you about today. All right, John, go ahead.
Welcome, everybody, and I'm glad you're here. We're going to talk about the role of science experiments in the classroom today. And I'm just going to go straight and share my screen and go right into the slideshow that I have to go with this talk. This is the third time, I think, that I've presented on this subject. And what I've noticed is that every time I present on the subject, I think of more things to say about it. So it's kind of still expanding, but I'm going to go ahead and share my screen now with you. And you should now see my first slide. What are labs for? Experiments as apprenticeship. If you can't see that, then maybe mention it in the chat box so that we'll know. But okay. All right, Emily's telling me everything looks good. So let's start with an anecdote. About 4 or 5 years ago, there was an article that appeared in Physics Today on the subject of a study that had been done about what labs or what teachers think that the labs are for. And most of the teachers were of the opinion that the lab part was to reinforce concepts that are learned by students in the lecture. But the study showed that that wasn't happening, that the labs did a very poor job at reinforcing what students learned in the lecture. And then the rest of the article was about how can we do better at that. But this sent me on a completely different path, because I started thinking, well, maybe the purpose of the lab shouldn't be regarded as primarily to reinforce what the lecturer is doing. Maybe we should think of the lab as fulfilling some other role in science education. So here's what they do and they don't do. They don't enforce your lectures as well as you think. What they do, though, is they teach things that can't easily be taught in books. And they enforce or reinforce to the students details that matter. I'm going to talk about many of those. And very importantly, they do also promote character formation because of things like the need to show discipline, to take care, to be attentive, to be neat, to use good workmanship, and so on. There's a lot of these kinds of things that are part of forming character that don't come naturally to us, that need to be formed within us. Just by way of setting the stage before we keep moving, I want to mention for a moment what distinguishes a demonstration from an experiment. This is particularly helpful to mention for some of you who may be homeschooling, because this usually isn't clear to people until they've thought about it. in science, in most sciences, particularly physics and chemistry, I'll put it that way, not necessarily so much in biology, but and probably 50% for earth science, but the labs are quantitative in physics and chemistry. This means they involve taking data, and they involve making predictions, and they involve comparing the predictions to the experimental results. And that is not what's happening in a demonstration. You do a demo, you're just showing some effect, and it's typically not quantitative, like pouring vinegar on baking soda in that picture. So you see gas evolving, but you're not physically measuring the quantities involved. But in an experiment where it's quantitative and we are trying to make measurements, and that means you have to have apparatus that is set up that is sensitive enough, and you have to have measurement instruments that are precise and accurate enough so that you can measure the effects that you're looking for. And this has a huge bearing on the experiments that you do and on the equipment that is required. It's far more expensive and complicated to do experiments that are quantitative than it is when you're doing just a qualitative demo. So now let's talk about the measurements. Making accurate measurements is very hard. And this is something that is not at all apparent to students when they first enter into your science classroom. In fact, until they've experienced the consequences of low accuracy, it's unlikely that they'll really appreciate what the consequences could be. But at the heart and soul of an experiment is measurement. And small inaccuracies in the measurements can have huge implications, destructive implications for your data. Here's an example of that. I ran an optics lab for many years, and I developed an experiment in there to use a rectangular prism and a laser to interact with Snell's law. So the students would use protractors to measure the angle of incidence and the angle inside the prism after the refraction. And then they would put these angles in to Snell's law with the goal of computing the index of refraction and the speed of light inside the prism. What I discovered was that a 1 or 2 degree error in that angle measurement could result in 20 to 30% difference between what they calculate the index of refraction to be and what the value actually is. 20 to 30% error because of a 1 to 2 degree measurement error. And as almost everyone knows, making a 1 degree error when measuring with a protractor is really easy. So the word here that we want students to begin thinking about and experiencing is just how easy it is to obtain inaccurate results. It will happen all by itself. You don't have to even try. What you have to try hard to do is to make accurate measurements, as accurate as you can possibly make them. And moreover, to become like a police dog, sniffing out sources of error and then conveying this attitude to the students. I mean, it's one of the things I enjoy the most, running experiments over and over and over, year after year, was learning all the ways error can creep in. And hundreds of places. Maybe you've done an experiment from one of my books where we push a car out in the parking lot and measure its acceleration. It's called the soul of motion experiment. One year I was doing that experiment with students, and it was windier than normal. And with my Kia Soul with the hatchback flipped up, that was acting like a sail, and the wind was pushing on the car. And we got the worst results that year than we'd ever gotten. And it was very instructive to me because it didn't even occur to me that that would happen. But this is the kind of stuff that you learn in the classroom. and which is why it's so important, not in the classroom, in the lab. This is why it's so important to do the labs and to think about labs as an apprenticeship of master working with the apprentice. So, you know, in the medieval times, the apprentice was the one qualified to teach. Sorry, the master was the one qualified to teach the apprentices. And after some years of gaining skill, the apprentice would become a journeyman at the time that he was qualified to go out and do this work without supervision. And then when further skill and experience had been gained, that person, once he was ready to teach others, then he was a master in the guild or the craft. And that's how I like to think about the laboratory experience, is that I'm teaching students things that it's very difficult to learn from a book, and experiencing them themselves is the way to learn them. So we want students to appreciate how easily small errors creep in, like the measurements on the protractor that I was talking about a moment ago. The importance of being painstaking when you are setting up your apparatus, using proper technique for making measurements, like reading the liquid in a burette or a graduated cylinder at the bottom of the meniscus. And moreover, not just reading at the bottom of the meniscus, but knowing that your height of your head relative to the bottom of the meniscus makes a big difference. Move your head up and down 1 or 2 inches, and the measurement, the apparent measurement, will change significantly. And so how important it is to have your eye exactly on a line with the bottom of the meniscus so that you're reading it right in line. And I've countless times seen students casually reading from a burette or a graduated cylinder or even a meter stick. And if they're casual about it, I guarantee the measurement is going to be off. If it's a GC, it could be off a milliliter or 2, which could be 10 or it could be several percent of your measurement. Ditto with a meter stick. If you're doing one of those experiments where, you know, a car goes down a ramp or something, you have to measure how high it is at the beginning. It's very easy, just by moving your head a little bit, for your measurement to change by a millimeter or 2. And so introducing error. And so we constantly must help students to understand and appreciate these ways for error to creep in and to seek to eliminate these sources of error. Another thing we want them to appreciate is taking the time to do it right, which for teenagers is not exactly the thing that they're thinking about all the time. We want students to pay attention to the apparatus. Again, we're doing things that you're not going to get in the book, because that's not where they don't have apparatus in their hands at that time. But when they're in the lab and the apparatus is set up in front of them, now we can pay attention to the apparatus. We can pay attention to making the careful measurements. We can talk to students about specifications for different instruments that they're using. For example, thermometers typically have an immersion line, and when you're going to put it into a liquid or something, you want it to be immersed up to the immersion line, and otherwise your reading might be inaccurate. Or storing thermometers vertically in a rack so that they don't get little gaps in the alcohol in the capillary. And treating them carefully so that they don't get broken. We want them to be observant, and I'll talk in a moment about journaling our observations. And we want them to be to participate in the cleanup, the setup and the cleanup. And I know as a classroom teacher how precious time is, and it's easier sometimes to just tell the students, I'll clean this up later, you guys go on to your next class. But we need to teach stewardship, and that means we need them to be involved in the cleanup and not just walk out. and expecting us to do it. That means we need to plan the lab out well so that there's time for that cleanup to occur. Now let's talk about journaling for a minute. This is one of those things that you learn by doing it under the watchful eye of someone who already knows how to do it well. Students will typically forget to write the date in their lab journal. They will forget to write down the team members' names in the lab journal because they figure, I already know all the members of my team. Why do I need to write their names down? But sometimes you need to come back on another day to finish the lab activity, and different people might be there that day than there were the first day. So we're teaching scientific habits of mind. That's what we're doing. And the students, they're not thinking about developing scientific habits of mind. What they're thinking is that this is a canned activity. I just have to check off the boxes as I go through the procedure, and then I'll be done. And what we're after here is a completely different learning exercise. We want students to develop the kind of habits of mind that would be valuable if you're working in a scientific environment or an engineering environment or any kind of environment that where technical accuracy is called for. So that's why it's so important for us to be fastidious with our students about documenting everything. If they're taking data and they discover later that they need to redo part of the experiment because they discovered that they have some inaccurate data that needs to be done over again, well, that should be documented in the journal so that there's a complete, thorough record of everything that occurred in the lab, including what they observed, any important notes about the conditions, like that windy day in that experiment. That would have been a thing to put in the lab journal. And we want them to practice making proper tables in the journal. It's so common, isn't it, for students to make a measurement in, say, inches, and they know that they're not going to be permitted to put, to do the calculations in inches. They're going to have to convert their numbers to meters. So they go ahead and convert it and then write down meters in their lab journal. But that's not right. The original units of measure should be written down and then later converted in another column in the same table. But we need a detailed paper trail record from the experiment all the way to the finished report. Now, there are many, many other things that we can model by engaging with the students in a lab, things that don't come up in the lecture. So here's a list, just as many as I can think of, but once you start thinking about it, you just keep thinking of more things. How about proper chemical storage, which would entail correct labeling, correct groupings, careful cleanliness so that we don't have a bunch of chemicals sitting around looking like this, where we don't even know what's in the bottles and there's stuff spilling out everywhere, and containers that are damaged or beyond their lifetime. That's something that we want them to understand. Another would be proper waste disposal. There are things you can pour down the drain. If you made some salt water or sugar water, you can just pour it down the drain. There are other things you're not going to pour down the drain, and we want them to know that you need to know the difference. We don't want to pour copper sulfate down the drain. We don't want to pour lead ions down the drain. So we need to go through, this comes up in a lab because you have the materials right in front of you, and now you have to do something with it during the cleanup. That's why we want them to be engaged in the cleanup and not just walk away. When you're just talking about the stoichiometry, you're not thinking about what would I actually do if I had some lead acetate that I was working with, and I need to know whether it's harmful in the environment, and if it is, what do I do with it? Sometimes I can let things evaporate. Sometimes I need to take it to a hazardous waste collection facility. These questions come up when we're doing the lab together. And so this is, again, it's not something that's being reinforced from the lecture. It's a different kind of thing that's being modeled. Proper behavior in a lab is another one. This should be learned, of course, by students before they ever even get to 7th grade. We don't want rambunctious and ornery teenagers misbehaving in a lab where there's glassware and delicate specimens and things like that sitting around. Tidiness is another thing that we need to communicate. And of course, for students and teachers alike, there are two kinds of people. There are slobs, and there are people who are very, very fastidious. And there are some people who are in between. But in a lab, we all need to be fastidious, and we all need to discipline ourselves so that we learn to be fastidious. It just doesn't do to have spillage on the countertop sitting around waiting to get into your lab journal, or apparatus that's set up in a cumbersome or messy fashion. We need everything to be set up neatly so that safety is not an issue, or safety problems don't come up and become issues. Here's another one: exhibiting the proper degree of respect for hazardous substances. Things like knowing that 10 molar hydrochloric acid is a fearsome chemical, and if you're carrying a bottle of it across the room, you'd better carry it as if it were a live baby, because if you drop it, really, really bad things will happen. And finally, on this slide, preparation of standard solutions is another thing that we might read about in the lecture portion, how to make this solution. But when we're doing it, we're combining the theory of how to make a standard solution with some new things. We're having to make measurements. We're using a volumetric flask, which may not ever even be mentioned in the lecture, and how we want to, and how we need to do it carefully and properly so that we have the right quantities involved. And here are some more things that can come up in the apprentice time of the laboratory practicum. Following safety practices, of course, is a big one. And a big one of those in a chemistry classroom will be never pouring water into a concentrated acid or base. When one does this, huge amounts of heat are generated, and the acid or base can flash right out of the container into your face. This would be a terrible thing if concentrated acid were to splash out onto a person. So we have, I hope you do, but in our lab, we have lots of safety practices. We review them regularly, and I hold all the students accountable for being aware of the safety practices. In my optics lab, I had a specific list of safety practices that applied in there, and the students were wonderful about knowing those rules and abiding by them. And so it was always very rewarding to me to see them holding each other accountable for using proper safety protocols when you're working with lasers. I've impressed upon each of them when they first came to work in that lab, that some of the lasers we have in there can cause permanent blindness if you are hit in the eye with the beam, and that gets their attention. So we need to be, but even if you're just working with blocks of wood in a physics lab of some kind where there's nothing dangerous, still we're, again, developing habits of mind, scientific habits of mind. And that means you get in the science lab mode, and you stay in that mode, and you don't get messy. You don't put your goggles up on your forehead and then forget about them up there. And you don't unbutton your lab coat because it's a little warm in here. You're careful to put on your nitrile gloves at every appropriate moment. And you're holding each other accountable for that as well. Here's some other things that would come up in a lab that wouldn't come up in a lecture. Learning how to use new equipment would be one. Years ago, when I was an undergraduate, I learned how to use an oscilloscope, but back then they were all analog oscilloscopes. And so when I got my first digital oscilloscope, I had no idea how to make it work. And I had to figure out how to make it work. Now, I knew enough about the way a scope worked that I didn't think I needed to get out the instruction manual and read it. So, but that meant having the attitude of, I can figure this out. I know what kind of adjustments I need to be able to make. It's a matter of finding the right menu buttons and so on, so that I can learn how to use this new version of a tool that I have some prior familiarity with. Learning to use parts and supply catalogs. This doesn't come up all the time. In fact, most labs don't have opportunities to teach things like this, unless you have lab assistants. Maybe some students are serving as assistants to help you in your lab. If so, and that would be great if you do, then when you need to reorder some materials, then you could get your students to help you do that. Of course, nowadays, a lot of materials catalogs are online, but I still prefer, for some applications, for tools, for example, or optics parts in my optics lab, I prefer the catalogs, the big, thick paper catalogs. And there are several ways to look things up: by the descriptive name or by the part number in the different indices, and then learning how to look at these tables of data and figure out which part you want is the right part number. These are very valuable experiences that, I mean, as an engineer, I use those kind of, that kind of skill all the time, ordering parts and supplies and apparatus. Another area where it's helpful to have someone working with you is in the preparation and construction of apparatus. And I wish in schools we had more opportunities to do this. I intentionally designed some of the experiments in our Novari Physical Science to use jigs that you could make, because if it's possible, I wanted students to have an opportunity to use tools and help make the apparatus, because this is a thing that scientists generally do. In graduate school, I worked in a lab one time where I got the privilege of learning how to use a metal lathe to machine some parts that we needed for these devices that we were making. And I was really excited about that, because I wanted to know how to use a lathe for a long time. And learning how to use it was a treat. But notice what we're doing here. When we're setting up apparatus or building it, we're giving students opportunities to use their hands and opportunities to use tools, and to develop the skills of craftsmanship that go along with that. And these skills are getting rarer and rarer these days, because students in particular, are spending so much time on electronic devices instead of working with their hands. So it's important that we take every opportunity and find opportunities, look for opportunities to help students use their hands and use tools, and to show them the proper ways to do it and the safety precautions they need to take, and so on. I've hurt myself a lot of times using tools, and it's just so easy to cut yourself or stick a screwdriver into the palm of your hand. And students need to learn by us showing them that it's a bad idea to hold that piece of metal in your palm of your hand and try to turn a screw into it with a screwdriver, because if it slips, it's just going to go right into your palm. And we need to show them the right way to do it by holding it some other way, so that if the screwdriver slips, it's not going to cause an injury. Finally, another item we can model for students is proper way to handle things like specimens or glassware. You don't want to break a $50 graduated cylinder just because you were not handling it properly. Or you don't want to break a valuable specimen from nature, like a sea star, because you weren't handling it properly. And again, these things should be learned prior to 7th grade as part of the grammar school science program. Another really big laboratory item where the master apprentice role relationship is so valuable is in the writing of the lab report. Frankly, students have no idea how to write a lab report until they're taught, and it's really hard to learn how to write well by reading a book. So what you need is you need someone to read your report, and they need to comment on it and give it back to you. And that's how you're going to learn to write more skillfully. Students don't know how to communicate their results very well. They don't know the value of reflecting on the results. They typically resist going beyond the obvious or the trivial. When they're told that if you have a percent difference that's very high, you need to speculate on factors that may have caused it and things that could be done to improve the results in the future. Without being taught otherwise, students will typically just throw out a bunch of random possibilities that couldn't possibly have the kind of effect that they are saying. And they need to be told not to do this. So, and held accountable for it. And if they are doing the car going down the ramp experiment and their calculated velocity comes out higher than what it should have, and they say, well, friction might have affected our result, then they need to be told, well, no, it can't. Friction can make your car go slower than you predicted that it would, but it can't make it go faster. So this is where an apprenticeship mentality is so important. You're showing and helping the student to write well. And this goes beyond, it includes grammar and spelling, but it goes so far beyond that. It's common in the procedure for students to refer to the car and the ramp as if the reader already knows what they're talking about. And if they did a correct job of writing the background section at the beginning, where they give a quick overview of the way the experiment is going to be conducted, then later, when they say the car and the ramp, it does make sense to the reader. But if that background section is missing, or if it's not written correctly, then the reader's thinking, what car? You haven't told me about a car yet. Taking care in the presentation so that the graphs look well and the report has a good professional appearance and the fonts are properly sized. I'm sure many of you have experienced reading reports that it's quite obvious the student didn't spend any time proofreading at all. So, or maybe their graph has a vertical line on it because all the data points are vertically stacked right above one another. That's why when I do labs, I have the students show me their graph a few days before the report is due to save them the agony of getting an F on a report because the graph was not figured out. And the value of report grading, here's where the master and apprentice relationship is so huge. And it takes so much time grading lab reports, but it's worth it because this is where you're really working one-on-one with a student to help that person develop the kind of writing abilities that's so important in any scientific context of any kind. In fact, more and more, it's obvious that people are benefit from being able to write well in any context, not just scientific or technical contexts. But certainly, if we just think in terms of science, engineering, and technical contexts like nursing or medical applications, being able to write well is very valuable. And knowing how to present your results, how to discuss them, how to draw conclusions that are relevant, and how to avoid saying things that are trite or trivial, statements like Galileo was an important man. Well, we shouldn't be saying things like that, and students should be told not to say things like that when they're even very young. Certainly by the time in their high school, they shouldn't say that. Of course he's important, otherwise we wouldn't be studying him. So they need to learn how to say things that are more substantive. One of the tips I like to use that speeds up the grading process is to develop my own set of editor's marks, so that I don't have to write out the problem, everywhere I see it. Now on this sample that you're looking at, the things on this slide are mostly things that I would write just as it's shown there. But other times, like if formatting is incorrect on a title for a graph or something, I might just use IF for improper formatting. And I've give them at the beginning of the year a list of the editor's marks, so they can look up for themselves. What does IF mean on this? Oh, it means improper format. So that can really speed up your grading process. And that is the end of my prepared remarks. So I'm going to stop the screen share and return to reality here, or virtual reality with you guys. And now we have time for Q&A. So I hope there will be some good questions. I guess I can anticipate one of them. I'm anticipating that there will be some people in this webinar that are homeschooling, and you hear this presentation on how to treat labs as an apprenticeship, which implies there's a master present, and you're not a science teacher, and you're not a scientist, and you're not an engineer. So you're not actually a master of using laboratory equipment and methods. So how does the apprenticeship role work in such a case? Well, I think it's important for us to recognize that there are some things that there is not a suitable replacement for when you're homeschooling. There are many advantages to homeschooling, but there are some things that are very difficult to deal with in a homeschooling environment. And this is one of them. You don't have a built-in expert in the lab, and you just have to do the best you can to find ways around it. Now, I can think of a long list of things you might do. You might co-op with other people and bring in an expert to help show us some of these things. Or you might Zoom with someone who can talk to you and help show you things. Or you can watch YouTube videos on how to do certain techniques, like there's a lot of videos on how to use a microscope, for example. And that's really easy if the teacher's standing there showing you how to use the microscope and walking you through the right procedure to make sure you don't damage anything, and to show you how to carry it, and so on. But in the absence of a teacher, there you can turn to the YouTube channel and look for videos that will help instruct you on that. Ditto for lots of science things. There are lots of science things on YouTube that you have access to. So there's no perfect answer to the question, how do I have an apprenticeship with this student at home in the absence of a teacher? The answer is you just have to get creative and leverage as many resources as you can. So with that, let's hear what some people's questions might be. Emily?
Okay, I am going through and answering a couple of these that are things I can provide links to. But I think if you want to just, it might be easiest if you read the questions yourself, and we can just go through them in order.
Okay.
And you can disregard.
What is the role of demos? That's the first one I see. Well, demos should be used constantly. I mean, almost every day there should be demonstrations in a science context. It's just that they can usually take place very quickly, and whereas an experiment takes a lot of planning and data collection, as I mentioned earlier. In my 9th grade classes, when I talk about that two objects, light and heavy, will fall at they'll accelerate at the same rate. One year it occurred to me that even though this is common knowledge for me, I thought, I bet these kids have never seen this happen. So I just on the spot said, have you guys seen this happen? Do you believe Galileo when he said everything accelerates at the same rate? And they just looked at me like, no. I said, all right, let's just do it right now. So I walked over to the supply cabinet and I got out 2 steel balls, one of them an inch diameter and one of them a 1/2 inch diameter. And I just climbed up on my desk and held my hands right up by the ceiling and said, watch the floor underneath my hand. So that all the kids put their heads down, watch the floor. I let go and the 2 balls hit at exactly the same time. And it was like the first time they'd ever seen it. Seeing made a difference to them, and way more than just hearing about it. So demos, very important and should happen almost every day. Okay, the next question. I guess that's my friend Dan Murphy who asked that first one. So glad to know you're here, Dan. Next, Terry Evers' question. Virtual instruction requires real commitment and investment on the part of the teacher to explain when correcting lab reports where the student made errors in their technique or recording measurements and so on. It is really laborious, but I know it's critical for mastery and to develop character traits and good habits. This is something parents seem often to complain about as though we are being nitpicky. Have you experienced pushback when you insist on this level of accuracy and detail? I wholeheartedly agree, but it's been a hard sell with parents. Well, I have never had the privilege of teaching in a virtual context, the way, not high school kids, only these webinars. And so those of you who for the last couple of years have had to do this, my hat goes off to you. I understand from everybody that it's just a heck of a lot of work. It wouldn't hurt to point out some of the things that I've mentioned in this webinar that are or in fact show people this webinar that, there's going to be a link to it. You could share it. The ideas that we're trying to communicate, like character formation, good habits, scientific habits of mind, the ease with which bad measurements occur, and so on. I mean, that's the message. And so, we're not being nitpicky. I regard this as a basic component of science education. It's not nitpicky. Just like it's not nitpicky for an art teacher to have certain expectations about how students are going to mix paint or store paint or things like that. It's not nitpicky when a football coach or some other sports coach has certain places that things are stored, certain ways of putting it there, certain places where you put your dirty gym clothes and you don't leave them in your locker to get all stinky. Okay, there are right ways of doing things in almost every area, and it's not being nitpicky to insist on them. So I hopefully this webinar will have given you some ideas that you can use to communicate that. I think I wrote a blog post about this one time, which may be out there on the Navarre Science and Math blog page. I haven't thought about that in a while, but that also might be a resource that you could share with parents that would help them to understand your point of view. Here's another question from Dan. How do you modify these criteria you talk about for younger students like 8th graders or even 6th graders? Lab journal, lab prep, and cleanup. Well, you do things at an age appropriate level, of course. I don't expect a high school lab journal to be maintained by a 10-year-old, but at the same time, we want to start students learning journaling when they're first holding a pencil in their hand. I've shared this story many times, but I remember being with a 2nd grade teacher one time where she told about having her 2nd graders out. They were doing a combination lesson that was combining poetry and science and English. It was all combined together. They went outside with their little journals, and these kids were supposed to make observations of plants and describe them. And she came up behind this little boy. I always tear up when I think about this. She came up behind this little boy and he had written, "The plant is green." And she said, well, what kind of green do you think that is? And this little 7-year-old kid said, well, I think it's celery green. And the teacher just said, yes, I think so too. It's celery green. Write that into your journal. So here she is teaching the 7th grader to use careful language to describe things. So this can start early. And, you know, in the old days when people were learning to be naturalists, drawing sketches of bugs and leaves and so on, that was such an important skill. That should be part of our training in grammar school as well. We should be teaching kids how to draw. Like that kid in Master and Commander, you know, who said he wanted to be a fighting naturalist. And, you know, he's being schooled by Stephen Maturin in drawing careful pictures of the bugs that he finds. If you haven't seen Master and Commander, well, it's intense, but I commend it to you. So lots of things we can do, and including cleanup and prep. I mean, everybody can learn how to clean their tabletop and put their, you know, wash out their bowls and stack them up in a certain place and dry them. So that should be a part of every lab as soon as kids are old enough to do those things. Galen, let's see here. My perspective on the Discovery Institute with Stephen Meyer, etc. Let's see here. What's the question? Let's see, the role that science and technology play in the culture and so on. So I think the question is just, what is my perspective on the Discovery Institute? I've read a lot of things published by the Discovery Institute from William Dembski, Stephen Meyer, and others. Just a Signature in the Cell is one that comes to mind. Very excellent book. There are some controversies associated with the Discovery Institute. I'm friends with lots of different institutes. I'm friends with Reasons to Believe. I'm friends with the Discovery Institute, and I'm even friends with BioLogos. Now, the reason I bring up BioLogos, even though some people don't like BioLogos, BioLogos, there are scientists writing with BioLogos who come from many different perspectives. And those different perspectives have different things to say about the Discovery Institute. Some people think that, that the whole idea of intelligent design research is silly because their understanding of the way God allowed the earth to unfold is entirely on its own according to the laws that he put in place. So that whereas the idea of design implies that intervention of some kind. I'm not going to get into those thorny issues. I'm just saying there are ways where different people have different points of view, and those are the places where Discovery Institute might be enforced and critiqued. There is one thing that I would critique them on. I've read a lot of the books on the intelligent design community, you know, collections of essays and so on that are purporting to take on evolutionary theory, but inevitably what they do is they take on atheism instead, and they conflate these two. And this has actually been quite frustrating to me to have these constantly conflated because they're completely separate and independent issues. And but I have a deep appreciation for much of what Discovery Institute people have done. Dan, here's another question about demonstrating safety practices by a negative example, like adding water to an acid to show what will happen. No, don't do that, Dan. What could happen is you get your eyeballs burned out, and I don't want that to happen. Just don't do that. I did it once because I wasn't paying attention, the very thing I want my students to do. And I dropped a few drops of water into a beaker that had a fairly concentrated acid in it. And all this started coming up out of the beaker, and I just instantly went, I can't believe I did that. That was stupid. I'm glad no one was here to see. Here I am confessing it to 71 people. But I don't do that. Sometimes people do really dumb things in YouTube videos. There's a demonstration that I referred to in physics modeling nature, where it's the collapse of a 55-gallon drum by boiling water in it and then sealing it off and then hosing it down, and then it eventually will implode in a very sudden fashion, scary, sudden fashion. But in the video, these people were walking up to it and trying to put ice cubes on it and stuff to cool it down. I just thought, get away from that thing, because when it goes, it's gonna. And sure enough, the people got away from it, and then it collapsed in a very violent fashion that could easily have injured someone. So I think let the YouTube videos be your negative examples if you like, but don't ever do it yourself. Don't ever do it live. Next question is the expectations for lab reports in grades 6 through 8. I think it's I like, and we do this in our own books. I like students to learn how to make graphs, to take the data and make the graphs and interact with some questions as a minimum. But then what a lot of middle school teachers do is have students one at a time on different experiments try their hand at writing different pieces of a report. So on the first experiment, maybe they'll write the background, and on the second experiment, they'll write a procedure. And here you can teach them how to write in third person during the procedure only, so that they, or first, either way, but not in the imperative mood. So you can teach them in that one section. Don't write like a recipe in the imperative mood. Either say, we, the team, did this and that, or say this and that were done. But that one section is where that's appropriate. And you can start pointing this out to them. But I don't see the need for students in the middle schools to do an entire report. I think that's too big of a task at that grade level. Pearl Kenny asks, John, would you address the frequency of lab reports for high school students who are new to writing reports? The right number is 5 or 6 per year. So 3 per semester, basically, but a lab report takes a couple of weeks, and you just can't do this for every experiment in biology. So our new biology book, the lab book, The Apprentice's Companion for General Biology, has got 38 activities in it. No way you can write a full report for every one of those. So what the teacher should do is select the 5 or 6 that are going to be treated with a full report. And then the rest can use a short form of some kind. And in that book, we provided the form itself, and in our chemistry experiments books as well. So use the short form for the other 15, 20, or 30 labs, and then for 5 or 6 of them, have them write a full report. Let's see here. Nicole says, how can the labs in the physical science book be adapted to a small space and with a homeschool? When I say small space, I mean really small space. We live on a sailboat. Ha! Okay, that's pretty small. Well, obviously you're not going to do the soul of motion lab, which is in the 9th grade books on a sailboat. I mean, a lot of labs are going to be hard to do on a sailboat because of the motion. So, maybe you can get creative. I know in Austin, there are businesses that rent space for an hour at a time. And nowadays, where everybody has, I mean, there are a lot of companies now renting space for office use. So maybe you can rent a 1 hour block of office time at a town where your boat is ported, and you can pull into the wharf, you can take your stuff, or you can even have it shipped to an address where you could go and set up in an office building in a lab or a room where you rented the room for a couple of hours, do the experiment or 2 or 3 experiments, maybe rent the thing for the whole day so that you can, you got to be more efficient, I guess, when you're living on a sailboat. But I mean, the physical science labs can all be done in a home, in a house or an apartment. I mean, that's where I was when I did them all, was in my own house. But on a sailboat makes it more challenging for sure. Terry says she makes a big deal about proper voice when writing scientifically. Is that worth it still, even for middle schoolers? Yes, answer is yes. And I discussed these voice and tense issues and person issues in the student lab report handbook. So if you haven't seen that yet, you should get that. I'd recommend that middle school teachers have a personal copy of the student lab report handbook and read through it so that you'll be educated yourself on the issues of tense and mood and voice, so that you can be working on this with your students, coaching them with it. And then, of course, once we get into high school, we want every student to have a copy of that and be reading it for himself or herself and learning how to write good lab reports. But yes, Terry, it is worth it. It is worth it. Some things just don't go away because of the internet, and these are things that don't go away. Will you provide a list of the editing remarks codes that I referenced? I tried looking for it the other day and I couldn't find it. Sorry, Missy. Just develop your own list as you go, and things that you have to write over and over again, learn a short way to denote it with just 2 or 3 letters and add it to your list, and type a paragraph that says, here's what I mean when I write that. And you can type that paragraph one time and then compile a list of these and get it to your students. Wish I still had the one that I was using, but I don't. Michelle.
I think this question must have come in an email yesterday.
Okay.
And Michelle shared it from someone.
This is about an in-person class. Okay, how many experiments would you suggest completing in this class scenario? So 5 to 6 per year for writing reports. In general chemistry, you want to do more than 5 or 6 experiments. I mean, our chemistry experiment books have 19 or 20 experiments in them. So I would encourage you to find creative ways to do more than just the 5 or 6. You definitely need them, have them write reports on that many, but there are ways that you can do more. Have them meet in groups, for example, with some kind of tutor or leader who could proctor that activity. So it's not in the in-person class necessarily, but it's being done. Just use your creativity to get that up. Chemistry experiments, I mean, I would do at least 15 during the school year. You might, the calorimetry experiment, or is it calorimetry? The one where you burn food and measure how much the water temperature goes up. That's an easy experiment to do at home independently. And yeah, you're lighting food on fire, but these are high school kids, so it shouldn't be a problem to light a marshmallow. And if the parent is worried that they might catch their hair on fire or something, they can stand there and monitor while they do that. But it's a one that students can do independently because the apparatus involved is very readily available and costs almost nothing. So some experiments like that one can be done, just tell the students to do it on their own. And they don't have to be part of the class scenario at all. All right, Katie Ruth says, what are some other ways to prepare students in grammar school for an apprenticeship experience in 7th grade and up? So in my book, From Wonder to Mastery, that has now replaced my older book, Teaching Science so that Students Learn Science, I provide in both those books a set of tables called Things Rising Seventh Graders Should Know. And there are 3 tables. One of them is knowledge, one of them is experiences, and one of them is skills. So I have a list of things on the skills list that students should know before they get into 7th grade. And one of them is careful handling of a specimen. One of them is proper behavior so that they're not being rambunctious and breaking things. So, there's many more on that list. So I encourage you to get a copy of that book and find that table. It'll have on it a lot more ideas there. Ellie Smith, do you have available a list of online schools, hybrid co-op schools that use Novare? Emily, do we have a list? I mean,
Sorry, I'm trying to keep myself muted because I don't want to be typing in people's ear, which I think I was doing earlier. Sorry if I was. But I don't think we have a complete list, Ellie, of schools who are using Novare, but we know of several. And the one that we always promote first is our own Scholé Academy. Scholé Academy is now doing a handful of Novare courses for the high school. They may already be full, but they are trying to add sections if those courses fill up. And I know there are, Wilson Hill is another one that uses Novare materials, but I don't think we have a complete list. Another good place to ask if you have a question about that is we have a Novare Facebook group, a closed Facebook group that many of you may be a part of already. If you go to Facebook and you search Novare Science Educator Support, Novare Science Educator Support on Facebook, you can request to join that group. I'm an administrator in that group and I can just let you in. And then that might be a really great place to ask that question for people who are enrolled in classes online. But Scholé Academy and Wilson Hill are 2 of them.
Back to our questions, Julie Draw, I think she must have typed very rapidly here, but I think that says, do students record the observations of a demo in a journal? So we journal our experiments, but what about journaling demonstrations? My answer to that is sometimes. Sometimes the demonstrations come and go really quickly, like that one about dropping the balls. So I don't require students to journal that, but other times we do demos that are more involved. And when we do that, I have them journal it. So you have to use your, you have to use your judgment on when that would be useful, but certainly you want students to be using their journals regularly. Sylvia's question is digital lab notebook. See the use of keeping a digital notebook, but struggling with having both a digital and a paper notebook. I'm not sure I have much advice to give on that. And that's because you're talking, I'm just totally old school. I use a computer and I try to be proficient at using my computer, and I type reports. Students are going to type the reports on the computer. And some of the data collection maybe would be done in a computer. Like if you were taking data with a computer using a sensor of some kind, and rather than writing down numbers, that would be helpful. But I still would have the paper notebook going on. I thought I saw a question from Ken Wogamuth, but I can't find it now. So I'm not sure if it was.
I think he had some comments in the chat box. He was just saying.
Oh, it was in the chat box. Okay.
Yeah. Thanks,
right.
Ken. We're glad you're here.
I didn't get to read it, but I'm glad to see you're here again, Ken. Michelle says she's interested in how the science curriculum adds in the classical element. How is it different from other curricula that doesn't claim to be classical? This science curriculum, I'm assuming that question pertains to the whole Navari curriculum and not just the lab activities. There are lots of things that make Navari classical, but read From Wonder to Mastery and you'll have it all laid out for you. It's inherently integrative. For starters, we're integrating mathematics and epistemology and history and language throughout everything. How do we integrate language? Well, one of the things is by writing lab reports from scratch. Another one is that all the questions in the book and on every test and quiz are questions where you have to answer either with a computation or with some memorized thing like drawing a Lewis structure. Or maybe it's not memorized, but you fill it out. You figure it out and draw the picture. Or it's a memorized thing like the chemical formula for something. Or it's a paragraph answer to a question. I call it a verbal question. What we don't use is fill in the blank and true, false, and multiple choice and all that, because it subverts the development of language development, which is one of the most important things there is, both according to classical education and just the Christian view of humans as language users who are serving a God who speaks things into creation and whose son is called the Word. So language is so important that it needs to permeate our instruction. And so I'm just giving you a quick list, Michelle, but there are many, many elements that make the curriculum classical. So there's a few. Here's an anonymous question. Is there enough safety information in favorite experiments for physics and physical science for a homeschool mom to be safe doing the experiments at home if the instructions are followed? I have this book and ASPC to use this fall, but I haven't read them. I can't remember about favorite experiments because it's all physics experiments where safety wasn't really the, I think on the experiment with the graduate. Yeah, okay. So here's an example. This is an experiment that's done in ASPC, and there's a safety issues section right here that talks about, because we're using glassware. And so I talk about glassware and thermometers and carelessness, silliness. I talk about tongs for handling beakers that are with hot liquids, and using eye protection when there's a burner flame going on in front of you. Always wearing eye protection. So yes, I think the answer is we got safety information for you when it's needed. Christy says, any ideas on what the advanced biology book would cover? The advanced biology book, here's my plan for that, if we ever get around to doing it, and while I'm still functioning. We want to reduce the amount of materials that's things like human organ systems that could be put in in life science. I want to expand the coverage of cell chemistry so that it's roughly half the course. So the idea behind advanced biology is for half the course to be cell chemistry. Dan, a fount of questions. How many lab reports per year for an 8th grade or lower? I wouldn't have them write any full-length reports. I would have them write something for every experiment, but it could just be turning in a graph and the data and their answers to 3 questions. That could be all that they do for a given report. So I would have them turn in something, but I wouldn't have them write a full lab report for anything at that grade level. Middle school life science course, Stephanie asks. Well, middle school life science is currently in the works, and we have 8 chapters, I think, from our author. And the first 3 are out to be reviewed by our review team. In other words, I've finished laying them out and then designing them and everything, and they're being read in their finished format. So we're hoping maybe 2 years. Where'd that question go? There it is. Yeah, we're hoping 2 years maybe to have that course out. So another anonymous question: if the advanced biology isn't out yet, do you recommend ASPC, then accelerated chemistry, and then the general biology? Well, that's one possible thing you could do. If I had a student, if I was a homeschooler and I had a student who didn't care at all about biology, but was totally into physics, then that is what I would do. Because general biology is a great book. And it's really fun to read and very informative, and it's got a lot of good biology in there. But on the other hand, if my student or students were already saying, man, I love this DNA stuff, I really want to be study biology in college, well, then I would use a different book. I'd use a more advanced cell biology type text that we don't have yet. And I would just go find one and use it. So for many people, the general biology text is a good option. So I'll leave it at that. Are the labs written for a 60-minute class, 90-minute class, longer? Oh, usually, now biology is different, but all the physics and chemistry ones are usually written with the assumption that the class lasts for 50 to 55 minutes. And there are some of the ones in the Apprentice's Companion for General Biology take longer than that. So you have to do them in over a period of a couple of days. Or some of them are short pieces, but they occur over like documenting a plant as it grows, a bean, mung bean, and drawing it and measuring it on a daily basis or a weekly basis as it goes. So that's, it's kind of everywhere, but all the physics and chemistry are, okay, so Ashley says ASPC and CAS. Yeah, those are all going to be 55-minute target for the length of the labs. Nicole says, how are labs dealt with in the Scolay Academy? I don't know the answer to that question, but I'm sure the Scolay Academy people do. So I'm going to have to refer you to them on that one. And we're down to the last question. Carl Dickin, hello. Michael, I haven't seen you in a while. Good to know you're here. He says, we've been using general biology text to guide our grade 7 life science class and has worked well. Thus, when they are exposed to general biology and biology, they have a nice transition. That's a nice idea. Anonymous says, do you recommend doing experiments and or demos first, having the students wonder what happened, or after they've been instructed and being taught so that they can see the outcome matches what they learned? Both. And I mix it up. I am not a person who does it the same way for everything I do, because some things work better one way and some things work better another way. I do at all times seek to inculcate in the students the attitude of asking why rather than asking to see it again. So when they see something fabulous happen, wow, do it again is the typical response, but that's an immature response, right? Aristotle talked about the weakness of spectacle, and we don't want our classes to be mere spectacle. So what we want students to think when they see something amazing is, wow, why did it do that? That's the question that's based on wonder. Wonder takes you deeper, and the deeper you go, the more wonder becomes. It's a positive feedback loop. The deeper you go, the more wondrous things are, and the more wondrous they are, the deeper you want to go. So, when I blow up coffee creamer, which is a lovely demonstration that has to be done out in a football field with, everybody 100 feet away and all that. And that demo is in favorite experiments in case you're interested. But the coffee creamer goes off like a cannon. I mean, it's just a complete, just cannon with a 40-foot ball of flames. So it's very cool. And but we've already studied the chemistry of combustion before that demo is done. So that's a case where I do the lecture in advance and the demonstration follows. Now, I think one of the places where this question kind of comes from is the whole idea of discovery learning, or another way to put it is the constructivist philosophy about education, where students need to do an experiment always first, so that motivates their study, and then they go into the theoretical details after the fact. And I don't agree with the usual formulation of how that works. There are lots of things going on in my classroom that are constructivist, even if my experiment occurs after the lecture. For example, learning how to solve problems in physics is a constructivist thing to do. You can't learn it by watching me work the problems on the board. That I can work them all, and they're all easy. They all look easy when I work them. So you have to work them for yourself. And when you do, you'll find out just how hard it is and all the things you can do to make it go wrong. So it's the student learning themselves how to solve the problems during doing it. So, there's a lot more to say on that topic, but I guess the short answer is that I would mix it up.
We should probably start wrapping it up. Sorry to interrupt you. I want to make sure I get a chance to share just a couple of links and things with you guys before we sign off today. So I dropped in the chat box a minute ago several links. John's been talking about a number of resources that we have available, and I put them in there just a minute ago. So we have our student lab report handbook, which you can find at classicalacademicpress.com. That is our technical writing guide for labs. Very helpful. It's been mentioned several times this afternoon. John's new book, From Wonder to Mastery, that just came out in May. And I saw a question pop up about this a minute ago that I answered. Yes, that does replace teaching science so that students learn science. So that if you read that book a number of years ago, this book is an updated version. It's longer, it's got more things, it's got more mastery-oriented research. So that is hot off the press as of May. So get yourself one of those. You can find that at CAP's website as well. And then John's course, Teaching Science Classically, I think is a good thing to reference here. That is on classicalu.com. And you can preview the first two sessions, the introductory session and the first lesson, for free. And you can subscribe to Classical U for a small fee each month, and that gives you access to the entire database of Classical U courses if you are interested to learn more about how we would teach science classically, which of course includes our Novare curriculum. And then a few things I just wanted to share my screen quickly with you and show you some more resources that we have. Okay, so this webinar the link for this webinar will be sent out on Tuesday, so keep an eye on your email for that. We have a Classical Academic Press YouTube channel, and on this YouTube channel, you can go to playlists.
Hey, the Q&A box is in the middle.
What's that?
The Q&A box is in the middle.
Oh, Q&A box. Hello, Q&A box. I'll just thank you. That's weird. I didn't know it would include that box. Is that better?
Well, it's still in the middle of the screen. Oh, that's my Q&A box. Sorry. I
can't even see my Q&A box right now.
Sorry, I interrupted you. Go ahead.
Oh, well, okay. I'm sorry, my Q&A box I can't even see it on my screen.
It's not there. It's not there.
Okay.
It was me.
Anyway, So we have this YouTube channel, and you can go to playlists and webinars here. And then we have our Classical Insights blog, which is at classicalacademicpress.com. And there's a little nice tab up here on the right, Education blog. And there are a number of science-oriented blogs here, including Science Experiments in an Online Environment, which may be helpful to some of you. And then we also have just, here's the whole Novare line. You can go to classicalacademicpress.com, resources, product lines, and then you can go to Novare, and that will give you everything here. And here is John's Classical U course, Teaching Science Classically. And you can see here the first 2 sessions. You can preview this content. So that'll give you an idea of what that looks like. Okay, I think that's all I wanted to share with my screen here. If we did not get to your question today, please email us at info@classicalsubjects.com. We want to make sure you get your help that you need and your questions answered. Are there any closing remarks you wanted to make?
Oh, thank you for your kind remarks. Those of you who've said things in the chat bar, I haven't been reading them all because I was talking, but I see a few here that are it's just, I cry all the time, but it's a blessing being able to do things like this. So thank you for your very kind comments. And I wish you guys a good year this year. It's a time for us to be praying. When something like this happens, COVID, that's causing so much pain, so much suffering, it's a time for us to be in prayer. So be in prayer for your students, be in prayer for their families, be in prayer for their health, be in prayer for your whole school, and others that God puts on your heart. Always seek to follow him. And thanks for letting me be a small part of that. That's it.
Thank you. Thank you. Thank you for joining us today.